Okay, hi everyone. Yeah, thank you so much for, first of all, I'm really excited that the seminars have started again, and thank you for inviting me to give a talk. So as Miguel said, the goal here is to get as many questions as possible. So the format of the slides are really simple, and I'm counting on everyone to ask a lot of questions. So feel free to interrupt me whenever you want, or you can just ask questions after the talk, whichever works better for you. So today I want to talk about this work, and so this is I just also want to mention that this is a result of a lot of really fruitful discussions with a lot of people, but specifically Georges Ovid. Like the discussions were very, very helpful in developing this, and this is about a connection between holography and how it strongly motivates TCC and the distance conjecture. And because some of I'm sure most of the people here are familiar with everything, all the requirements that I'm going to say, but I'm going to spend like a very few short slides to go over everything that I'm going to be using so that everyone's on the same page. All right, so this is Swampland seminars, the Swampland program. The goal is to find some universal properties, some universal principles that are satisfied by all the non-anomalous EFDs that have quantum gravity UV completion. So the idea is that when you add gravity to the mix of your quantum theory, there are some criteria that are satisfied, and if we can find these, then we can limit the space of EFDs in a gravitational theory. And today I'm going to be focusing on two conjectures in particular. So let me just briefly review the statements of the conjectures. So the first one is distance conjecture. And the statement of the distance conjecture is that if you take a scalar field in your theory and take its vacuum expectation value to infinity, take a modulus of your theory and take its vacuum expectation value to infinity, then there's a tower of light weakly coupled states. Both the fact that they're light and weakly coupled is important. Moreover, the masses of these states depend exponentially on the scalar field phi, and here the scalar field is canonically normalized, meaning that its kinetic term is canonically normalized. And lastly, this constant c, which determines how quickly the masses of these particles are going to zero, there's a universal minimum for c, meaning that it cannot be that this is true for the lightest tower, and meaning that it cannot be that all the states can remain arbitrarily slow moving, like their masses can remain arbitrarily, their dependence remain arbitrarily slow in terms of your scalar field. So there's a universal upper bound on how quickly the masses go to zero for the lightest tower. And this is a paper, you can see it. And the core of the distance conjecture is really that it captures the essence of duality, meaning that if you, for example, go into different limits of the moduli space, in one limit you get a tower of light weakly coupled particles that provide one weakly coupled description for that corner of the moduli space, and different corner you get a different description. And the fact that these two descriptions share a moduli space is different way of saying that you have two dual descriptions. So really at its core, it's capturing dualities. Okay, and then the other conjecture that we'll be focusing on is the Trans-Planckian censorship conjecture. And this statement, the phrasing of the conjecture is dynamical, is in terms of the dynamics that your theory allows or doesn't allow. And the conjecture is that if you have a gravitational theory, if you have a consistent quantum gravity, then it cannot, your theory cannot host a solution where your universe has a cosmological expansion that is fast enough and lasts long enough, such that if you start with Planckian-sized quantum fluctuations, these quantum fluctuations will exit the Hubble horizon and classicalize. So this is the statement of the conjecture. Now, I'll come back to the motivations for the conjectures later, but the statement of the conjecture is this, that you cannot have a cosmological expansion that is long and fast enough that your Planck-sized fluctuations exit the Hubble horizon. And if you want to, yep.
Sorry, could I ask a quick question? How do you distinguish cosmological horizon from black hole horizon? In black hole horizon, you would expect to have this small right? This is the Trans-Planckian problem. These
Yeah.
small modes are the ones that end up becoming the low wavelength Hawking radiation away from the black hole, right?
Good question. So the classicalization is one of the differences. The Hawking radiation is not classical, but when these radiations exit the Hubble horizon, they become classical. Yeah. Does that answer your question? I mean, again, this is not the reason that necessarily TCC is correct, but yeah, that's one.
No, I understand it. Just
yeah. Thanks. So and if you want to put this in terms of an equation, we can write it in this form where L Planck is the initial wavelength of your quantum fluctuations, AF over AI. A here is a scale factor, AF is at a final time, AI is at an initial time. This is your wavelength after the expansion, and you want to keep this below the Hubble radius at the final time. So this would be how you can write it. Any questions about the statements of the conjectures? Okay. So let's just quickly see what TCC implies, but we don't want to get into a lot of details, but just get an intuition about what it actually says. So TCC clearly is saying that you cannot have a cosmological expansion, that lasts too long. So it should either be become slow, or somehow at some point it should suddenly stop, or something needs to happen to it. Now, if you have a scalar potential, there are three different scenarios that you can realize a cosmological expansion. One of them is that you can have your scalar field stuck in a metastable de Sitter. The other one is unstable de Sitter, which, subject to quantum fluctuation, it will exit this unstable equilibrium. Or you can have a quintessence-like model here. Now, for metastable de Sitter, one of the ways that TCC can be satisfied is that the lifetime associated to tunneling out of that metastable minimum is smaller than this time scale. And for this time scale, we often refer to it as a TCC time scale. And you'll see that it's slightly different from Hubble time. It has this logarithmic correction. And thanks to this logarithmic correction, this is in our universe greater than the age of our universe. So if we're stuck in a metastable minimum, and if TCC is correct, we can thank this logarithm for it. Now, as for unstable potential, as for this local maximum of the potential, you can guess that probably the kind of constraint TCC gives you is that the second derivative should be large enough so that the potential will be steep around that local maximum, so that will roll down. And you can find the derivation in the original paper. Here, A and B are some constants that depend on dimension. And finally, when you have this kind of rolling behavior, what you find is that TCC tells you that the potential should decay exponentially fast. And there is so V should be smaller than or equal to some e to minus lambda phi, which this lambda only depends on dimension. And I'll come back to what the value of this lambda here is. Okay. Now, as for the value of lambda, so in the original paper, we kind of considered two cases. The first case is if the tower of particles that might become light and might get excited can be ignored. In other words, you can say that if their masses is greater than the Hubble scale, so their excitations can be ignored. In that case, the lambda that TCC gives you is 2 over square root of d minus 2. So it tells you that the potential must decay faster than e to the minus this constant times phi. Now, however, the other case, the other possibility that we considered was that if there is a light tower that is lighter or equal to the Hubble scale, and because of that, it can get excited. And so now, because of the emergent string conjecture, if we trust emergent string conjecture, we can argue that. So this was done in this paper by Tom Rodelius, that you can say that whether the light tower is KK tower or it's a string tower, it never happens that the mass is smaller than h. So very, very likely always the tower is greater than h. You can have this marginal case where m is of the order of h, but modulo that, you can say that the mass of the lightest tower is always heavier than Hubble. So TCC roughly tells you modulo that marginal case of lambda must be greater than 2 over square root of d minus 2. Okay, now I focus on these two conjectures, and one of the reasons that these two conjectures are interesting is that they're phenomenologically important. They have some implications, strong implications actually, for cosmology, in particular for inflation. So both of these conjectures cause trouble for inflationary models to some extent. Now, the distance conjecture caused problem for inflation because it's telling you that if you take the value of scalar field and you move it by a lot, then you get all these light towers that now you have to take into account for your dynamics. But typically, in at least the conventional old inflationary models, you have this very long Trans-Planckian field range for your scalar field to make sure that you get 60 folds of inflation. Now, there are ways to avoid that, but the conventional models are somewhat in tension with distance conjecture. Now, TCC is even more in tension with inflation, and it's kind of it's right on the surface. It's very easy to see why, because the whole idea of inflation is that you have the scalar field that's creating this long-lasting de Sitter-like expansion, exponential expansion that solves all different kinds of problems, but including generating the quantum fluctuations that then we enter the Hubble horizon and we see as CMB fluctuations. But what that requires, if you don't want to get initial condition problems, is to have Planckian fluctuations exit the Hubble horizon, and that's exactly what TCC prohibits. So because of that, you can already guess that TCC imposes really strong conditions, and these were, at least for these single field cold inflationary models, these constraints were found in this paper, and you can see that the upper bounds on both the energy scale, but more importantly, the field range are very severe. And for example, when you have such a small field range for your inflationary model to work, you would need to tune in the initial condition very precisely, because typically the idea is that you don't have to tune in the initial condition. It will eventually go to the slow roll solution, because that's the attractor. But if your field range is too small, that's not going to happen. So you run
Alek,
into
one question. Can you remind me where the 10 to the minus 31 and Planck is coming from exactly? Like, what are you imposing there?
So this is consistency with observation. Just structure formation, making sure that the structure, the wavelengths required for the structure formation come from the fluctuations within the Hubble scale in the time of inflation, and then you impose TCC on it.
Mm-hmm.
Any other question? Okay, so this is all to say that these two conjectures are, and this was just one example, but these two conjectures are phenomenologically relevant. Typically the conjectures, and I think Hiroshi has a famous graph that the conjectures that are more phenomenologically useful are usually less rigorous in the Swampland program. So, and this is why we want to focus on these two conjectures specifically TCC, which is maybe less rigorous than some of the other conjectures, but it's very phenomenologically important. And that's the focus of my talk today, to see how we can motivate these conjectures. So how do we typically motivate Swampland conjectures? What are the different types of motivations that we come up with? So one of them is that they're somehow connected to some more fundamental principle, something like unitarity and causality, something like black hole physics, something like ADS-CFT. Now, we have two examples of this. Here I list two examples of this. The first one is how you can relate the mild version of weak gravity conjecture to unitarity, for example, of quantum field theory. Some theories just asking that your scattering amplitudes are unitary, those put some constraints on the partial wave decomposition coefficients, and those in turn put some constraints on the coefficients of higher order derivatives. And they turn out to modify the extremality condition for black holes exactly in agreement with mild weak gravity conjecture. So that's one example where you can relate one of these Swampland conjectures to something like unitarity. And The other famous example is so this is by Daniel Harlow and Hiroshi Guri, that you can connect no global symmetry conjecture to ADS CFD, for example, and in the context of ADS, it's very nicely you can see that it's almost baked into holography that all kind of global symmetries of the boundary theory are always gauged. Sorry, gauged in the bulk. So that's one type of evidence. Now, the other type of evidence is by examples. So we have string theory, we have many different constructions in string theory, and the question is that can we, like, how consistent string theory is with a particular conjecture, and how non-trivial that consistency is. Is it something that we see and it's non-trivial, or is it something that it's obvious that it should have been? Now, for TCC, we have a lot of consistency conditions, like a lot of consistency like this. We have many different constructions in string theory with these exponentially decaying scalar potentials. And in all of them, we see that the lambda that they give satisfies the inequality that I mentioned earlier. So these are just some examples of these constructions. And another example of a Swampland conjecture that, I mean, among other motivations for it, it also has evidence from string theory, is the completeness of spectrum, that the charge lattice of your gauge theory completely appears in the theory. Okay. Now, and the last type of evidence that we find, which is often very surprising, is consistency among this network of Swampland conjectures. So there are more established Swampland conjectures like no global symmetry conjecture, and sometimes, for example, you see very non-trivial connections between these Swampland conjectures that tell you, connect some of the maybe less established ones to more established ones. And for example, there's a deep connection between no global symmetry conjecture and completeness of spectrum. There's a very beautiful paper that you can read. And for TCC, for example, there's also several of these connections, and one of them, which we studied in a work with Kamran, Iran, and Miguel, was that if you have a potential, if you have a potential with several metastable minima, and you consider these transitions, these tunnelings from one metastable to another one, and you assume that the domain wall that carries out this transition is charged under a top form symmetry, then it turns out that the TCC imposed on this tunneling implies the weak gravity conjecture for this domain wall. So this is the higher form generalization of the weak gravity conjecture. That's a really surprising connection that happens to be there. Okay, now for TCC, we have a lot of non-trivial evidence from string theory. We have connection to other Swampland conjectures. And the goal is to connect it also to some fundamental principle, like unitarity, like holography, something like that. Any questions so far? Okay. All right, so let's see if we can connect TCC to something more fundamental. And here I want to focus on holography, and this is a very general, very basic version of holography in some sense, which I'll explain more carefully now. So in quantum gravity, we believe that there are no local observables. And this is a schematic picture that shows that in quantum gravity, we think that I mean, there are different arguments for it, but this is one of the arguments, that you have to sum over different topologies. In fact, there's also a nice paper by Jake McNamara that explains how these, gravitational solitons, these summing over topologies, actually play a very important role in the consistency of with several other Swampland conjectures. So in quantum gravity, we think that you should sum over different topologies, and if that's the case, then that means that the manifold of space-time, it's not something you start with to formulate the theory, but it's something emergent. And therefore, you shouldn't start with a theory that assumes the manifold and then has local operators defined on top of that structure, but all of that structure should somehow emerge. Another example of this is T-duality, that how when you go from one description to a T-dual description, observables that are local in one description suddenly emerge. It's not that they're local in the other one, they're actually a combination of the winding operators in the other one. But the description suddenly emerges. So this is to say that the local structure shouldn't be the building block, the definition of the theory, but it should be something that emerges. Yeah, so when we sum over different topologies, there's one of them that becomes dominant, and then that's what defines what our spacetime is. Okay, but if we don't have local observables, then how do we define a quantum gravity? So usually when we have a non-compact universe, a non-compact spacetime, the way that we define quantum gravity is via some boundary observables. Now, these boundary observables can take different shapes and forms, but that's the thing that quantum gravity gives us, and then we can define effective field theory and all of those based on these boundary observables. For example, string theory gives us these worldsheet amplitudes that by definition are boundary observables. So string theory, the output of string theory is always these boundary observables. And then the way you can think of effective field theory in the context of string theory is that the thing that effective field theory effectively describes are the boundary observables. So you do some worldsheet calculations, you find some boundary observables, and then you write down an EFD that effectively describes those boundary observables. Okay, and really that's the basic that's the kind of core of holography, that this is what's kind of different between gravitational theories and non-gravitational theories, that the way you want to define your theory in a gravitational theory is via these boundary observables. And there are different types of boundary observables. In flat space, you can have scattering amplitudes. In ADS, you can have boundary correlators. And in de Sitter, we don't know whether or not this exists, but if eternal de Sitter exists, for one possible boundary observable that you can have in it is these boundary correlators in the SCFD. Now, so here it seems that we have a variety of boundary observables, but in the next few slides, I want to convince you that these are actually all the same thing. There's a universal way of looking at it that would tell you that if you have an effective field theory in a given background, what are the boundary observables? And these are all really very similar. Okay, let's start with the simplest case. Let's start with flat space. And here I'm starting really with the simplest, like hand wavy case of, let's say, like a free scalar field, something like that. Now, in the case of scalar field, we can actually not free, weakly coupled, but a scalar field. So in the case of scalar field, there is a way to define scattering amplitudes from the correlation functions, and that's given by the LSD formula. And it's given by, so you just take the correlation function, you calculate it in the momentum space, and then you look at the poles of these correlation functions, and those poles are determine your S matrix. Now, I want to rearrange this equation in a way that's very suggestive of what's that universal equation that's true for all these different backgrounds. So let me rearrange it like this. So on this expression in the first line, I've just written it like this, where phi tilde is the Fourier transform of phi. And here P1, P2, Pn, these are the off-shell momenta. And this expression here, I've moved it to the other side, and I've written it as the inverse of the propagator, but in the momentum space. And then here you have the S matrix. So the expression on the left side is the S matrix. I've just written it on purpose in this way, but it's really just the S matrix. And the capital P's here are unshell momenta. So these are d-1 dimensional vectors, but the small p's here, these are off-shell momenta. So these are d-dimensional. And the way to go from the d-dimensional off-shell momenta to d-1 dimensional, we can call it boundary because it has one less dimension, is by multiplying this correlation function by the inverse of propagator and then taking the limit of your off-shell momentum going to on-shell. Okay. Now let's go to the ADS space. So in ADS space, you take these correlation functions in your effective field theory. And so these are the space-time, the bulk correlation functions. And yet then you take the limit of the points of these field operators, their location going towards the boundary. And when you take their position towards the boundary, there is some non-trivial, oscillation, some non-trivial dependence on position. So you make sure to factor that out, to cancel out that part, to make the whole thing converge to something. And to do that, you multiply by the inverse of the propagator, the boundary bulk propagator. And then this limit would give you the boundary correlation function. So you see, the general idea is to take this d-dimensional field operator, and by d-dimensional, I mean the position depends on d coordinates, and then take the limit of that point either in position space or momentum space, going to some d-1 dimensional subspace, and then take out its trivial kind of dependence by multiplying by the inverse of propagator, and that will make sure that it converges to something. And that's your kind of boundary observable. And the same thing is true in the SCFD correspondence. So assuming that something like eternal de Sitter exists, as a curious EFD statement, it's true that if you have an EFD in de Sitter space, you can generate these boundary correlators. And again, the way you do it is very similar to the ADS correlators. You just follow the same procedure. And the answer might be a little different, but the procedure is identical.
Alek,
yeah.
I guess what we gain by this procedure of sending things to the boundary is that gravity decouples. Like we're making gravitational effects arbitrarily weak, both in the de Sitter, the flat spaces matrix, and the ADS boundary.
Yes. Although you can also say that, I mean, for example, in the flat space case, you don't have to have gravity to define scattering amplitude. But it's true that when you do that, you're also diluting the gravitational interaction, but also all the other sort of gauge interactions. So
right. Yeah, we have a synthetically free state. Yeah, I guess.
Yeah. Thank you. So we have, so this is just to show you that, the way of finding boundary observables in an EFT and non-compact space is really almost kind of one equation. And you choose whether to go with momentum space or the position space based on whether your particles can make it to future infinity, or based on whether your particles localize in momentum space or your particles localize in position space. Based on that, you choose whether to go with this or this. For example, in flat space, your particles, as they move to infinity, their momentum localizes in momentum space, but their position is still changing. So you go with the first one. But in DSCFD, as you get this expansion of universe, your particle's position, the co-moving position localizes. So you go with this one, but their momentum changes. And you can see that the equations other than that are very similar. Here you have d-dimensional parameters. Here you have d-1 dimensional parameters. And then you multiply by the inverse propagator. And this is why we draw amputated diagrams. Any questions? Okay. All right. So this is how we find boundary observables in EFT. And a boundary definition of effective field theory is that it's the effective field theory is defined to give you the right boundary observables. In other words, quantum gravity produces the boundary data, and then you find the EFT that correctly estimates those boundary data. So this is one way to define an effective field theory. And this is the way that we define effective field theory in string theory. String theory produces the string worldsheet amplitudes for us, and then the EFT is chosen so that it correctly reproduces those string worldsheet amplitudes. There's a different way of defining EFT, which is in non-gravitational theories. You can just define it, pick your way of defining a quantum field theory, algebraic or not, but it's to really think of OFX as a local observable and think of that local structure as being the the defining identity of your theory. And this is not what we use in gravitational theories. So, I mean, I already give you one reason that why, quantum gravity is defined in terms of boundary observables, but there are other reasons that specifically work for positive potentials, which I will get back to after, like in Q&A. If you're curious, please ask me. Yeah. Okay. Any other questions about these points so far? All right. Okay, so now that we understood how to define boundary theories in a given spacetime, we want to apply it to a very specific type of spacetime, a spacetime that emerges a lot in string theory. And these are these kind of expansionary spacetimes that are resulted of that are results of these kind of quintessence models with exponential potentials. So for now, let's just focus on a general expansionary FRW solution with some scale factor that depends on time. And first, we want to just get some intuition about whether or not our correct boundary observable is a scattering amplitude or it's a frozen correlator. How should we define that d-1 dimensional parameter space for the boundary observables? And the idea is that, again, you have scattering amplitudes when the particles kind of only localize in momentum space. So in this case, we would say that when they make it to spatial infinity, and you have frozen correlators when your particle freeze in position and co-moving position, and they do not make it to spatial infinity. This is a very clear distinction. So before doing field theory calculation, we want to do a hand-wavy particle calculation, like a very, very simple calculation. And I mean, later we'll see that it matches completely with the more involved field theory calculation, but it's a good way to get some intuition. Now, also before doing the calculation, let me also add one more thing, that for boundary correlators to be non-trivial, to have some information for this boundary data, to have some information in it, I require two things from it. The first one is that I want it to depend on initial conditions. If I change my initial condition and the boundary observable turns out to be the same, always, regardless of what's going on in the bulk, then it means that it doesn't see what's going on in the bulk. Therefore, the bulk is not a construction of that boundary data. So this is a very modest requirement of the boundary observable, that it cares about that bulk data. And the second one is that we want it, again, to be non-trivial. So we want it to vanish for x not equal to y. We don't want it to just be 0. We know that it never vanishes for x equals to y because in those cases you have collinear singularities. So that we know that it never vanishes. But we want it to carry some non-trivial information. So if we have frozen correlators, we want to make sure that it's not just delta function, for example. Okay, now let's do the back of the envelope calculation that I mentioned earlier. So we want to see when we should define scattering amplitudes and when we should define frozen correlators. And to do that, we want to determine whether our particles with a given mass m will make its way to infinity or not. So if you have a massive particle, late in the expansion, its momentum gets redshifted, and then you can calculate its velocity, and you can integrate that velocity to see if it, the velocity from now to infinity, if it gives you some finite distance or if it goes all the way to infinity. And you'll see that the condition that it does not make it to infinity is given by ma² greater than t. Now I'll come back to cases where m itself is time dependent, and this equation will still be trustable. But yeah, so this is the condition. If for massive particles ma² is bigger than t, or in other words, it scales faster than t, then your expansion is so fast that the redshift is so fast that your particle does not make it to spatial infinity. So you should expect to have some frozen correlation functions here. Otherwise, scattering amplitudes. Now, for massless particles, it's a little simpler. The geodesic is just, you can easily solve for it. dt equals a dx, and what you find is that if a scales faster than t, in other words, if the acceleration is if the expansion is accelerated, then it does not make it to spatial infinity, and you should end up with frozen correlation functions. Okay. Now, at the end of it, we want to relate this to a statement about scalar potentials. So let's also see what's the connection here. So if you have a scalar potential that goes like e to the minus lambda phi, it turns out that this will always give you a polynomial expansion. And this will turn out to be a very important feature, that there's a difference between polynomial expansion and exponential expansion. And the p here, which is the rate of this expansion, or the exponent of t, depends on the lambda here. And if lambda, for lambda smaller than some value, as you increase lambda, So for lambda smaller than some value, because most of the Hubble energy is dominated by your potential energy. When you increase lambda, that means that your potential is going faster, is going quicker to zero. And because of that, the Hubble scale is going to zero quicker. Therefore, the expansion is slower. Therefore, as you increase lambda, p goes down. But for lambda large enough, what happens is that suddenly the energy is dominated by the kinetic energy, and then the potential is not that irrelevant anymore, and then the p stays fixed. Okay, but the key point is that for all exponential potentials, you get polynomial expansion. That's one thing that I want you to remember from the slide. Okay, now let's do, again, this is like a really simple QFT calculation. So what do we want to calculate? We want to consider a scalar field. We want to solve for, the Green's function and the correlation functions. And we want to see, in the cases where we know we have to get these frozen correlators, what are those frozen correlators? Are they something like ADS CFD or DS CFD? Is it a CFD correlator? What is that correlator? Is it non-trivial? So first we write down the equation of motion. Then we find the quasi-stationary solutions at late times. So these are just the steps of the calculation. Then we do mode expansion in terms of those quasi-stationary solutions. We get these creation and annihilation operators. Then we use the canonical commutation relations of phi and its conjugate momentum to find the canonical commutation relations for alpha and alpha dagger. So these creation and annihilation operators. And as you can see, they're very similar to normal QFT. And at the end of it, when you do all this calculation, you find that for the cases where the correlation functions freeze out, it's always trivial. And this is really the punchline. This is the main result, that in these polynomial expansions, whenever you do not have scattering amplitude, whenever your correlation functions freeze out, they freeze out to something that carries no information about the bulk. So you cannot define that effective field theory using boundary observables.
Sorry, Alek, can I ask about that?
Please.
So here what you're talking about is a very subtle effect that so I guess what I wanted to ask is, if I do correlators at any finite time, not matter how large, then I can still see things. And I guess what I'm asking is, have you made sure that there's not like a different G that you need to strip off so that the correlators are also well defined in the limit? Or maybe also, in ADS-CFT, sometimes when we want to construct local operators in the bulk, we actually need non-local operators in the boundary. Could it be that you could have non-local operators giving you non-trivial correlators? Or yeah, I guess that is really, to me, the physical question that, if I do it very, very late, then it's okay, I can measure everything, but not at infinite times.
That's a great question. So as you said, for any finite time, if you're a bulk observer, this is just normal EFD. If you have precise enough measurements, then you'll be able to see it. But this is really the statement that at the boundary, like if strictly speaking, you want to define your observables at the boundary, then you cannot do that. And this is a very valid question that, for example, could Could it be that if we scale these operators differently, we can get something convergent and will behave? If we use different coordinate system, if instead of taking the co-moving coordinate system, I take some x that has a different time dependence, can I get something well defined there? And these are two important questions. So let me answer each one of them separately. So the first one, in terms of the scaling of phi, in order for your correlation functions to converge to something, you have to always divide by the inverse, multiply by the inverse propagator to make sure that you get the right singularity structure when these are collinear. So that's really determined by the equation that I showed earlier. So that's the scaling of phi. But then you can ask, okay, I know that, for example, if I don't use co-moving coordinates, if I use just the proper coordinates, of course, the correlation function is not going to go to 0. This is just a 2-point correlation in flat space. Now, the problem with that is that this type of correlation function, although does not go to 0, it also loses information about the initial condition. In other words, it does not depend on initial condition. Now, the reason for that is because of the expansion. When you keep the proper distance fixed, all the modes that you're probing are modes that at some point in the past were Trans-Planckian. And as they emerge from that Trans-Planckian regime, you want to put them in the vacuum state. And because of that, you don't measure anything about the initial state. So the very fact that you want your correlation functions capture non-trivial information about the initial state forces on you that you have to work with the co-moving coordinates, because these are the modes, these are the coordinates that move with the expansion of your wavelengths. Does that...
Yes, just follow-up question. How is this, what you just said, different for de Sitter?
Great question, and I think that's in the next slide or one of the next slides. But that's amazing question. Yeah, maybe not next. Yeah, in one more slide, I'll get to it. But yeah, so let's just recap the results. So we said that if in these polynomial expansions, if you get frozen correlators, they always happen to be trivial. So really the way to go is to only have scattering amplitudes. Now, it turns out that means that P must be always smaller than 1. In other words, if P is greater than 1, if you have accelerated expansion, you always get frozen correlators, and those are trivial. So that's not allowed. However, for massive particles, there's a way to to play with the mass. You can also say that, well, what if the mass depends on time? And that's actually a very reasonable scenario because of the distance conjecture. Because of distance conjecture, you have the scalar field that moves, and the masses of the light particles also depend on that scalar field and depend on time. So what about that? So when you do the calculation carefully, you find that there's this connection between mass and time, and you see that the mass of the particles should also decay fast enough. And I'll come back to the consequences of this in a second. So, but this is the summary of the results. So, a few remarks. The same results apply to higher spin particles. You can easily generalize the calculation. The correlation function. So this is something that I said, that the correlation functions need to depend on the initial state, and in fact, in this case, they do depend on the initial state, but they also they just depend trivially, in that they just factorize. Yeah. So here these results apply to weakly coupled particles, which admit some EFD description, because here we're using the EFD description, but this applies to all of them. So not only the massless spectrum, it also depends to all the other particles. And finally, Miguel's question, that exponential expansion changes this whole calculation in a very major way. So the math of it is that in the equation of motion, you'll see different terms dominate when the expansion is exponential. But to get some intuition about what's different about it is that exponential expansion is a different, like qualitatively different type of expansion. And it's so fast that if you take 2 points on the boundary or near the boundary, you have to move in the bulk for a much shorter time for them to be in the same Hubble patch. Therefore, they interact with each other at a much smaller depth in the bulk. And because of that, the interaction between the boundary correlators in some sense is much stronger when you have a faster type of expansion. And in fact, in de Sitter space, where you have exponential expansion, you do not get trivial data, and that's the whole basis for DSCFT. So in a second, I'll show that what we've found is equivalent to TCC. However, I'll make the distinction that this is only equivalent to TCC for these type of polynomial expansions. So for example, I cannot rule out eternal de Sitter using this, because eternal de Sitter has boundary observables. Whether or not those have some UV complete realization, that's a different question, but I cannot at least rule it out using this. And also, I want to mention that, I mean, in a second, we'll come to TCC, but this is very much in the spirit of TCC, because TCC, like the motivation for it was kind of that if you have this expansion that's very fast, you'll lose quantum information. And this is very much in the same spirit. So TCC. If you have some scale factor that depends polynomially in time, I'll finish in a few minutes. I know that I'm over time, but so if you have a scale factor that depends polynomially in time, in this equation you can clearly see that that corresponds to p smaller than or equal to 1, because 1 over Hubble goes like time, and the left-hand side goes like t to the p. So you want p smaller than or equal to 1. So p smaller than to equal to 1, which is a condition we found before, is TCC for these scalar field cosmologies. And that also implies that lambda must be greater than 2 over square root of t minus 2. So in these exponential potentials, satisfying TCC is simply the statement that you can have a boundary definition for your theory. And this must be satisfied for string theory constructions, because if not, what is it that you're calculating? The world sheet amplitudes are nothing, not like they don't get connected to your EFD at all. So it's actually a consistency condition for anything you get in string theory. Now, for the cases where mass depends on time, you want to see that if this is, or how this is connected to distance conjecture. I'll just show you the result, that this condition here tells you that the mass should decay quickly enough. And if you assume that the mass goes like e to the minus c phi, you'll find that the c that you get from here is related to lambda. And for different lambdas, you get different values of c. And the strongest condition that you'll find for all different values of lambda is for lambda that is that marginal case of 2 over square root of t minus 2. And for that, the c that you find is 1 over square root of t minus 2. And it's very interesting that this is exactly the coefficient that comes up in sharpened distance conjecture, but it comes from a completely different origin. Yeah.
Alek, one question. So
Yep.
I should think of applying this condition only to the particles that are becoming massless, not the ones that become heavy, or
yeah. So
they will violate it, no? So
yeah. So we should really only, because here we use field theory to, we're saying that suppose you have an effective field theory description, then what are the boundary observables? So those particles need to admit some effective field theory. And for example, as long as their masses is smaller or equal to species scale, you can do that. For example, in the case of ADS-CFT, the KK particles are much smaller than the species scale, so you can apply this to those. But for example, if you have particles that their masses is shooting up and they become, it's not really a statement about whether their masses is going to 0. It's a statement about whether or not they're weakly coupled enough to admit EFD description. In other words, whether or not their masses is smaller than or equal to the species scale. And because the species scale is also going to 0, then you want to look at particles that are becoming light.
Mm-hmm. And then, so this is actually also stronger result than the sharpened bound from Ben, Tom, and company. Because this applies to all the towers becoming light, right? So the result is only the leading tower, but you could have other towers that have a smaller value of the exponential rate.
Yes and no. So let me say in what sense it's stronger, and then in what sense it's weaker. It's stronger in the sense that if you have multiple towers that, as you said, that you have like multiple towers and one of them is not the leading tower, but has a particle with a mass scale smaller than the species scale, then you can apply this to that too. So in that sense, it's stronger. But in some other sense, it's weaker in that the C that we find here is actually not always bigger than 1 over square root of t minus 2. 1 over square root of t minus 2 is the strongest one. So it's actually always smaller than 1 over square root of t minus 2. So in that sense, it's weaker.
So the exponential root can be smaller than this.
Yes, yes.
And that
So the
happens
upper
when?
bound is a weaker upper bound, but it applies to more particles.
And how do I distinguish when I can get a smaller exponential rate than 1 over the square root of d minus 2?
So this 1 over square root of d minus 2 is really the strongest one that you can get. So, I see. So C here only depends on lambda. So I surveyed different lambdas and I saw which one will give you the strongest C.
Okay, so different behaviors of the potential.
Yes, yes, it depends on the behavior of potential.
So if the potential, and when is the situation in which the exponential rate of the tower can be lower, when the exponential rate of the potential is larger or lower?
When the exponential potential is actually smaller, when it's flatter, and this is the flattest it can be, the condition that you find is stronger. Yeah.
Okay. Thanks.
And thank you. Yeah.